Okay, let's do some filter design and start with the bandstop notch filter. Bandstop notch filter. And how to design that one. First, we need to know our sampling rate. Well, usually these filters are done for a digital sampling system and, for example, a microcontroller, and for slow signals, say 1000 hertz is just quite enough for most of the measurement systems. If you have audio, then of course you need to go higher sampling rate, but that's good for, say, any normal measurement. Then it also gives you some room to do some digital filtering. Analog filter is expensive because it always takes some printed circuit board print out. Salin key structure. The second pole Salin key has one operational amplifier and two capacitors and two resistors, right? With gain, you have then 4 resistors. Is it like that? I should know that by heart. Salin key. Yeah, that's a Salin key. Unity gate, yes. So 2 capacitors, 2 resistors, those take some printed circuit board space, and if you have, say, 8th order, you have already 16 passive components plus 4 operational amplifiers. That takes that much space. What? 1 square centimeter, at least. Okay, the same in software takes this much code, not more than that. It still fits on 1 page if you do it smart. Okay, so sampling rate. This is a measurement system, maybe a data logger, and then our usual the notch frequency Fn is 100 hertz. This is the 100 hertz, the line humming, or in some countries 120 hertz. But anyways, the harmonic of 50 hertz. Okay, the corresponding. We need to know the corresponding omega. Omega n. 2 times pi times fs. No, fn divided by fs. How did I put it? Yeah, fn divided by fs. Yes, there. So this is the angular frequency. Okay, and that's where our zeros are. And zeros, basically, I will mark them ZZ equals 2. We need a 0 pair. First is the on unit circle J times omega n. That's the first 0 location. Then we need a complex omega. Let me change that one. Omega n. Okay. Try again. So that's just one single 0, but we always need also the complex conjugate pair. Otherwise, you cannot get real numbers for the as the system coefficients. all of those special places must be either on the real axis or as complex conjugate pairs to get, back to the real numbers on the system coefficients. Okay, z. Then we need another z, and I can do it, for example, like this: z semicolon. So this will be actually a column vector and complex conjugate of z. Okay, complex conjugate pair. There we go. And now I can actually show this one as at the moment, basically poles are both, there are two poles and they are both at 0. I don't have the poles set yet. And I can take a look at the z-plane, ZZ, PP. There we go. So that's the Argand diagram for the system. The system coefficients. You might be also interested about that one. How to get back to the system coefficients from roots. So these are roots. We have already done the from system coefficients to the roots. The same thing backwards, meaning the system coefficients BB equals polynomial, which is defined by these roots. I'll just print those out. Polynomial coefficients defined by these roots. There we go. Ha! Oh, that's nice. There are two of those numbers are 1, and then there's that one which is not that nice, 1.6180. Oh, there might be even more digits, meaning that it's not, when you put this one on microcontroller, you will never get exactly the same answer, which means, okay, these knots might change a little bit on the realization because the calculation accuracy. But let's not worry about it. Now we have the floating point accuracy, and I think on this microcontroller you are using, it also has the floating point unit on it. Does it? It has. My recommendation, do the calculations with the floating point. It's so much easier. On 8-bit processors or some of these, say, weird 16-bit processors, the floating point operations are done by software. Then you cannot do any real filtering with those. With the sampling rate of 1000 samples per second, that's also your calculation rate. For every single input you need to do on the second order system, you need to do 4 multiplications and 5 additions minimum. Okay. So basically, I have tested one of these 8-bit RISC computers, processors. It's Cypress M8 core. Oh no, yes, M8 core, which runs at 24 megahertz clock rate. You might think that that's fast, but it can actually do only 200 floating point operations in a second. Okay, meaning about 40 samples per second sampling rate only for digital filtering second pole. Okay, so but that's your ARM processor if it has a floating point. Well, you might test it first. How fast does it go with the debugging tools? It's easy. Just have a counter counting how many points, and then you basically set a timer for 1 second and just run a multiplication on the loop and just count, then basically the loop counter after 1 second gives you exactly the performance. It'll be enough. I think it can do about 10 megaflops also in that range. Okay, anyway, so that's the numerator polynomial. Then denominator polynomial, let's calculate also those, which are basically, since we have poles. Okay, as you can see, A0 equals 1. Okay, common mistakes actually here is to set the, on some of these filter designs, you set the A0 to 0. Not a good idea, then you don't know how to calculate the y of n. Okay, so I have filter coefficients. I can do results. I can do filtering, but also I can do the frequency response of system BBAA 1024 points and sampling rate. There we go. There we are. We have a notch at 100 Hertz. However, as I said to you, it resembles more like that, not this one yet. Let's fix that one. So set the half width of the notch as 10 Hertz. 10 Hertz is also then the delta omega d omega equals 2 times pi times 10 Hertz divided by Fs. So this, whoops, what happened? There. Okay. Delta omega, which is also setting the distance of that pole location to the unit circle. So now we can fix the poles, which is 1 minus delta omega, that's the range from origin, times ZZ. It would be on the same angle. Okay. And let's do the Z-plane again. There we go. Yeah, it looks like those. Let's see. So the 0 and pole are on the same angle, and that would be the 3 dB point distance. All right. So that's Z-plane done. What we need to do, we recalculate the polynomial coefficients for the feedback term, and now we have non-zero delay. So this is IIR system. Well, yeah, it's IIR because the poles are not at the origin. So also the feedback is required to do that one. And frequency response of this system is something like that. It's pretty good actually. It removes 100 Hertz signal, and then actually the 3 dB distance here is about 10 Hertz and 10 Hertz at 20 Hertz bandwidth of a notch filter. That's pretty good. So 20 Hertz. Oh, let's see. That's 100. So Q factor is 5. It's a pretty good filter. And only, well, 5 multiplications, 4 additions. No, it does not have since B. See, B equals, what was my B? B was there. So it has 2 of these are already 1. So 1 multiplication, 2, 3 multiplications, and 4 additions. pretty cost-efficient digital filter, and also quite nice performance on frequencies axis. On the amplitude spectrum, but the phase angle will be, well, something else. Okay, good. So that's the notch filter. Next, let me get a tool to design more filters. By the way, since you have the floating point, the arithmetics, then how to make the filter implementation, second order filter implementation. Have you any idea? I will give you a little bit of glue there. You can actually take a look at some libraries for that processor. There's two different kind of filter implementations already there. Also for the fixed arithmetics, 16-byte fixed arithmetic, or I think 32 8 bits. I'm not sure. But anyhow, since you have a signal coming in, that's well, time-based signal, and that goes into your, well, amplification already, or probably on this microcontroller unit, and then you have the sampling A to D converter. Sampling clock comes from somewhere. Make sure that you set up the sampling rate correctly. Follow the guidelines of what the datasheet gives. And this gives you that 12-bit A to D conversion result. 12 bits. Okay. 12 bits means about 80 dB dynamic range. Not more than that. That's about 80 dB. Okay, which one factor on designing your filter? Okay, then you have the second order system. Second order system coefficients from, for example, Matlab. You can actually just take these, let's see, like this printf. We are familiar with C programming, right? Actually, I could also do the sprintf, I think. Does it have sprintf? No? Well, we can always open a file. Open. Okay, home. Oops. Home. File identifier is equal to open coefs.h and for writing. Correct? Maybe? Yep. 10 file ID. Okay. Now I opened a coefs.h file for writing. Now I can basically do fprintf. FID format specification, same way as you would do on C programming. So %G, I will just do it the easy way, comma, and then you put here the parameters A, for example, AA. Does it work? Maybe. And then, okay, maybe I will add here the a line, new line, maybe BB. Let's see what happens, and then close FID. And let me take a quick look what the coefs actually looks like. Okay, I can live with that. So basically I can now edit it a little bit and do the, so these are my coefficient vectors for BB and AA. Double BB, no wait, that's AA. AA 2 equals and cha, right. Double BB, or also, well, no, three values. Three values are from, and okay, so this is the old school of type making the getting these parameters out to the this formatted string coefs file. Okay, so let me just save it. This is one way of doing it. And for that kind of simple notch filter, maybe this is the fastest way also. And of course, you can take as many floating point decimals there as you wish. Okay, next part. So that's now you have the filter coefficients A and B, which are just double AA 3 members, and BB has also the 3 values there. Now you basically need the filtering function. You need to make the filter implementation. My recommendation is not to use the same format as Matlab, since you need to have a specific filter with exactly those. And only thing that which comes in is the input data and output data. So double vector of input and then const double of vector for output. This is to prevent any side effects on the function. Okay, and this would be local variables or even local constants for this filter. And then remember, okay, the second order, it doesn't make any difference if you what kind of calculations you do here. Well, my suggestion is to just write down basically this one. B2 x n minus 2 minus A1 y n minus 1, and then we take a closer look, minus A2 y n minus 2, what we have in here. What is actually required in addition to these input values is local memory of the old values. You need memory of those. When you are doing the filter, I don't care, or nobody else cares if that local memory is already stored in here on those values, or is it stored as static values in here. So x1, x2, y1, y2. This is one way of doing it. So you have the previous values stored like this. What makes a huge difference, though, on the performance? Okay, now this goes into details of the embedded systems programming. If you have the system so that you have the A to D conversion done, well, A to D conversion is done at rate fs, then it goes to the main loop. Okay, the idle loop. The question is actually how to treat these data. I would do block filtering. So you have a counter here. Okay, CO++. Counter also, which counts how many samples you have already got. And then basically counter is equal to some big number. Then you go and do filtering in a block. Return to idle. Okay, so otherwise what happens? Have you gone through the microprocessor architectures or processor architectures and pipelining? What happens to pipelining if you have a basically the timer interrupts? So most of the thing what your system is doing is timer interrupts. So basically everything starts happening after the time interrupt. So if you are running low on resources, then basically analyzing every single time step one by time would destroy your pipelining of those tasks. So it would be more efficient to wait for, say, enough of samples and then basically do block processing of that sample. Then this DSP operations would be done in a nice pipeline way with a fixed, basically here that would have a fixed for loop, I from 0 to I less than a number n, I plus plus. So if this is a fixed number, then the compiler does pretty good on pipelining the stuff on all of those. Does it have 4 cores or single core? Single. Okay, well it doesn't make any difference. It doesn't do the parallel, but in principle it could. If you had the core M3, that's quad core. I don't remember. Those ARM processor architects, so those are well, that's the fast processor though. But anyway, so yeah, that goes here. So see, this is how easy it is. Okay. It gets more sense out of this one when you start actually doing it. So just remember, the sampling is the key thing for this signal processing. You must have a constant sampling rate. Then the filtering part is basically easy. Then when you do the filtering, well, the simplest way of doing filtering would be take one data at a time and then just analyze it and do it. But on the other hand, it destroys the resources of your microprocessor. So instead, you might actually wait for a few samples and then filter a block. And of course, you will be also consuming the data after filtering, I would guess. So is there also D2A? Probably. Well, and that also have the sampling there. Okay, timer interrupts. Okay, have you had some other course already about which has had timer interrupts? Just in case, you know, my German colleague forgets, when you have interrupt service routine, it should do as little as possible. As little as possible. As simple as possible. But not simpler than that. Who said that? Henry Ford. No, not Henry Ford. Thomas Alva Edison. You must do everything as simple. If you get this filter working. Okay, and my job is actually to ensure that you have a filter to work with. So you now basically you have the well, you can do the FIR filters easily. FIR filter coefficients with windowing method. You just have the this impulse response part. So you only have BB there. A is just 1 and no feedback. And then you have a long multiplication, which is a convolution between data and the filter coefficients. And filter coefficients you can write the same way as we did here. Okay. This IIR systems. IIR systems are sections always as second order systems when you do the implementation. Otherwise, basically, if you do multiple orders, more than second order section then you will start having the bad effects of rounding errors. Okay, with the FIR system, it's not that critical actually. And on FIR system, it works quite the opposite. Since in principle, you are calculating the weighted average of signal. Weighted average meaning you are improving the statistics of the signal. Okay. All right. So now I have some hints how to get these data out of MATLAB. Well, some hints how to write your code. Well, that looks ugly. Good luck. But then now the design tool for filtering. It used to be called FDA tool, but I just noticed that the MathWorks has changed it as filter designer. Filter and then capital letter D, designer. Let's see, does it start? Does it work also for you? Filter designer. It should start up this kind of window. If it gives you a hard time, then you didn't copy that part of the distribution yet. Then you might actually try the FDA tool. It might be there instead. But did you get this one? Yeah, it takes for a while too. When you open it first time, it sets up parameters. Filter, and then the capital D on the designer. Got it? Excellent. That's the ultimate tool for doing the filter design. Let me Make it a bit bigger. Hmm. Ah, why it doesn't there? There we go. There we go. Good. So, see the magic box. Same I wrote, draw you yesterday. So there's a band pass, a pass band, stop band, some frequencies. Everything starts from the fact that you basically first specify what is your sampling rate. Sampling rate, for example, say 8,000 hertz. Pass band, for example, at 1,000 hertz. Then stop band at 1,200 hertz. Making low pass minimum order. Okay, minimum order, it's basically this is optimizes and calculates the most cost efficient filter which fits into your design parameters. A stop, meaning the stop band attenuation. Well, 80 dB. Well, that will be perfect for 12 bits. So basically, you don't need to do any spectral analysis, since you know that okay, 80 hertz, whatever we had there, even that the full tilt will be removed below the least significant bit. Okay, it does not make any sense to put this one higher than 80, since actually, well, we don't have anything below 80 dB. Okay, design filter. There we go. And we have FIR equiripple filter. We can also select the Butterworth. Okay, now basically the system designs a using this analog model of Butterworth filter, using this as this magic box corners. Okay, there you have. And let's see what is the order number. Order number is 48. Think of analog filter with 48. No, thank you. All right. With 48, you're starting to get actually trouble with the calculation accuracies. But anyways, let's tweak it a little bit. I think this is overkill since, oh yeah, it's overkill. 1000 dB attenuation here. I don't think we need that much. I think we need say, I just tweak that part, say up to 4 kilohertz. Whoops. Wait, what happened? Oh, no, 4 kilohertz. Pass band. Oh, no. Not 4 kilohertz. That will be out there. There we go. It still is kind of overkill, but well, 12 order. That's fine. Another way of designing this one, I think your requirement on the on that course is to make second order system, second order filter. There we go. Or well, how about making the same but high pass filter? Click. This is so much fun. Band pass filter, higher cutoff, lower cutoff. Of course, they changed this one. So from 1000 hertz to 2000 hertz band pass filters, second order. Yep, click. This is so much fun. Band stop, even band stop you can do. Again, it's funny, right? How it, from 1000 to 2000 hertz. There we go. Looks like notch filter to me, but anyways, I might be wrong. So actually, you can do the either notch, direct notch placement or just pick of those one of the filters. Well, yeah, or if you are brave to do the fourth order, and then we can actually also select some other filters. So basically, when you have time, just play around with these tools, since practically this is almost the not that one. Oops. It's just stupid if I have to. There we go. So different kind of filters, but you can actually. I don't understand why they always change those to some default values. Okay, different kind of designs. Let me do a second order, for example, for that one. See, this would be quite close to what you are doing on the what is it? Chipset type 2 FS 8000. Well, this doesn't look correct. Does it? Okay. Yes, so basically, I need to go higher order number to get the passband somewhere in sensible place. Okay, good. But anyways, this is the whole analysis tool. So it means that it also have the well, this is the magnitude response is right there, but then we have the phase response, group delay. Okay, group delay in samples. Impulse response. Step response. Zero pole plot. So it has everything what you need. Just click. So, after 4 days, I finally show you this. You could have started using it already. But on the other hand, you wouldn't then understand what is behind of it. And then you actually, this is not the ultimate tool for everything. You still need to know what is behind of it. Okay. And this is actually excellent. So you have the filter coefficients as sections. So section 1, numerator and denominator, meaning numerator is B, denominator is A. And now we have two filter sections. So second order sections actually are always cascaded. Well, Matlab gives you cascaded section design. So you have the H1, Z, and then H2, Z. So if you are doing more than a second order system, you need to cascade these. So meaning that the input of the second one is actually getting input from the output of the first one. Cascade. That's what cascade means. So the systems in series. All right. Let's see. There's also something that you can also design with these. Okay, group multi-transforms. You can also see what this filter actually would look like in fixed point arithmetics. So set quantization parameters. Now everything is done with a double precision floating point number. But actually you can also see what if we go into fixed point presentation, meaning signed integer calculations. In small microcontrollers without the floating point unit, that would be the only way to go, since the software floating point calculations would take way too much time. So fixed point arithmetics, and we have 12-bit data, so 16 bits should be enough. Okay, so coefficients 16-bit, and then basically we can go and take a look at the magnitude responses of, yeah, so they're actually fitting right at the top of each other with 16-point arithmetic. So yeah, only a little bit of difference in here. We can also play around a little bit, although we have the say 12-bit data. How about if we have 12-bit coefficients? Apply. Do we get difference? No, still quite good. Okay, 8 bits. All right, now we start getting a little bit of difference here. So even with 8-bit coefficients, we can actually do pretty good calculations. Have you already gone through the FPGA design? On FPGAs, you can do whatever precision you want. The word length is actually up to you to fix. So you can go actually, for example, and do 6-bit arithmetics. Okay, now we are getting some difference. Some, say, remarkable difference. Okay, but actually this filter, particular filter, would work just fine with with this 16-bit fixed point presentation. Also, however, let's change the topology. Where was it? Now, this system is arranged as second-order sections, which means that the calculation accuracy is as good as it gets. If we convert this one to single section, meaning 4th degree single section, I think we are getting some difference, especially in here going to 8. Let's see. Yeah. Okay, there we go. So remember the 8-bit presentation was pretty good on the previous second-order sections, but however, if we go in the single section, meaning 4th degree single section, we are getting lots of error already on the quantized filter coefficients. And where that comes from, I will show you. It comes from these numbers. The numerator here has basically data ranging from 0024 to 001, okay? But denominator has 1 decade difference between highest and lowest the magnitude on those numbers. If we go into even higher degree systems, we would get even more difference on those numbers when we have a single section. But on second order sections, we have basically optimal calculation accuracy. So if possible, do the calculations on second order sections, especially on IIR. The IIR denominator fundamentally dictates the performance of IIR system. Okay, let's see. Let me take a quick look at today's exercise. So that's basically the last exercise for the 3 credit version. If you want 5 credits, then basically do also the next 2 exercises. Only one of them are now present there. However, so the first one is design a bandstop notch filter. Oops, hold on to do that. Bandstop notch filter. Second one is plot zeros and poles. Then impulse response 25 values. Then design IIR filter with the following properties. Okay, sampling rate, cutoff frequency, stop band attenuation, transit bandwidth, max 2 dB ripple, minimum order number. Well, it sounds like similar parameters what I saw on the this filter designer tool. Okay, write the commands actually. Let me see. Or provide a screen copy of the filter designer tool. And then verify your design from amplitude response graph. So give me also the okay with some amplitude response on the same graph. Compare this one with the FIR filter which you had done previously. What are the major differences? Major differences. IIR, FIR has some differences. Order number 1 is 1. The flatness and other things. Take a look at those. It's basically the amplitude responses or phase responses, and what are the major differences? Then design IIR high pass filter with the following properties. Okay, and then the 7 design the IIR filter to match the requirements you determined on the exercise 4.7. 4.7, the exercise is about doing the doing first the spectrum analysis of the sample, and then design the filter the filter parameterization, and then basically do the coefficients. And okay, comparing IIR and FIR again. Well, okay, that's wow. This is fun. Then you would do the kind of equalizer for your audio signal, the last part. That's actually fun. So sampling rate, CD quality audio 44.1 kilohertz. Bass, meaning from 0 to 200 hertz, the low frequencies. Middle frequencies are from 200 hertz to 2 kilohertz, and then the high frequencies are from 2 kilohertz to Nyquist rate. 3 different filter bands. one single input goes into 3 different filters. That's the high pass, band pass, and low pass. Each of those have gain, variable gain basically in real life, but you have fixed gain there. And then just add the signals together. That's your tone control for audio. And on our logarithmic scale, so that's 200 hertz, 2 kilohertz, 20 kilohertz, the audio bands. Okay, that's the low frequencies, middle frequencies, high frequencies. I'm not listening to those anymore. And the basically the tone control is only about having those 3 different bands and then adjusting the volume of each of those individually. Okay. Oh boy, Thomas will be surprised to see this kind of filter on the microcontroller. Haha. To get some, respect. Yeah. Oh, it's just a tone controller. Design filter. Well, it's your choice. IIRO, FIR, and this is 3-band equalizer with those values and transition bandwidth. Okay, if cutoff frequency divided by 5/4. So actually, that comes from the analog world. You basically fix this transition bandwidth so that in logarithmic scale they look about the similar. They'll be matching and 3 dB points, and then basically matching also the stop bands. Oh, so they will be balanced. Okay, and then just 30 dB minus 15 and 12 plus 12. So plus 30 dB minus 15 dB plus 12 dB gain. Yeah. And then basically put some voices there. If you put music, remember that use only legal music. Please don't sing yourself. Or yeah, well, you can. So that, but anyways, one good the source for noise is actually go into the center of Bonn and just record the noise from the streets. That's white noise, and you would hear the difference quite easily on a white noise. Okay, that's all for today's stuff, I think. Yeah. So I went through the theory, then some Matlab stuff with this nice filter designer tool, notch filter with this Matlab, and also showed you how to make how to print this data or filter coefficients from Matlab to any file. So that's my part of the show. Let me take a quick look. So it's the deadline for the first exercise is about 1 hour from now. And this far, I have got I have got only 4 returns, actually 3 returns, which have the, well, Clemens, Philip, Moritz, and Sven has returned. So 1, 2, 3, 5. Who hasn't returned anything yet? Or did you already do it? Let me take a quick look. Exercises. No, only those 4 names. So you still have time. Okay, good. Any questions? I'll be hanging around here until 1 o'clock. Then I have a train to catch. And I will start going through these exercise returns as soon as they come. Otherwise, the system was that, see, well, this scoreboard says it all. So to get the 3 credits from Metropolia, you need to return enough of points for 3 credits, meaning at least 20 points altogether to have the passing grade. But of course, you will be needing the stuff from especially exercise 4 and 5 on your rest of the course. You would also do those exercises. So please do it. You will also get some feedback from me, especially if there are some mistakes. I will give feedback, so you don't do the same mistakes on the microcontroller level anymore. On the other hand, there's a trick also that 3 credits also gives enough of points. If you do all of those, you will get probably enough of points for some, 40% of the 7 exercises. So, okay. So basically, you end up doing the 5 credit course. And to get a better grade on 5 credit course, which is Metropolia credits. I don't know if you are how seriously you would like to take the Metropolia credits from here. But anyways, the doing everything correct here would give you the grade 3, which is about the good grade already. Doing also those will give you chances to get the best possible grade. Exercise 6 is already there. It's about microcontroller. I will show you the exercise, which basically would be, say, rather nice exercise for your system. So it actually goes through the quantization of systems and exercise. Okay, let's see, what does it have? Is there band stop notch, calculate for 8-bit system, checking the stability, bandpass filter. So fundamentally, there's only difference up to here is that this one is that there's a quantization effect, which is taken care of the filter designer. You don't need to do the calculations much of the calculations yourself. And here, determine how many bits should be used in system, meaning the fixed point system, comparing to floating point. Okay. How many bits should be used if the system was implemented a second order section? Okay. Then this part 8 is about your processor platform, the performance of your processor platform. I recommend you to do some performance measurement or estimate before implementing your the filter. And then, okay, that's how many channels Raspberry Pi can, 3 can approximately manage running the previous filter. Yeah, we are using Raspberry Pi in Metropolia quite a lot, so that's why I had this nasty question there. It's quite high number actually. Raspberry Pi 3. It can handle quite a lot of analog channels if it was put only for that one and no operating system. Okay. And then measuring the performance of your laptop and estimate how many channels it can handle. For example, on Matlab. Okay. Just, running different kind of performance tests. The part of the embedded systems design is to find the cheapest possible processor to do the job. Good. So that's number 6. Number 7 exercise is not there yet. It used to be on system control. I know you hate system control. Every engineer student in the world hates system control. But anyways, there will be a less hateful topic of regression as the 7th exercise. Just wait for maybe 1 month or so. Okay, good. That's all. Any questions?